The aim with this video is to describe the 2019-2020 version of the course KETF40 Mass Transfer in Environmental Engineering in about 5 minutes. The course is 15 ECTS credits and stretches over 2 study periods, study period 2 and 3. Assessment is done through a written exam, compulsory tasks, labs and study visits. Let us first describe study period 2. There are 2 compulsory tasks and 1 lab in study period 2, the rest being assessed at a written exam with 6 exam tasks. It is possible to receive a pass on the first 3 exam tasks on process calculations and reaction engineering on a midterm exam, while the other 3 exam tasks on moist air, mass transfer and distillation is taken on the January exam. In the process calculation section, students learn to make steady-state mass balances for elements and for components. The rank of the element matrix and reaction matrix respectively is important, as that gives you either the number of independent element balances or the number of independent reactions. In process calculation, you get a system of linear equations that describe the steady state. By making a degree of freedom analysis and introducing a basis of calculation, you can determine if the system is solvable or not. Yield, selectivity and conversion are important terms in this section. In reaction engineering, the student learns to combine reaction rate expressions and the reaction orders with reactor mixing models by writing appropriate mass balances for the system. The mixing models include the continuously stirred tank reactor, CSTR, the batch reactor, the plug flow reactor, PFR, but we also deal with non-ideal reactors and residence time distributions. The compulsory task deals with degradation of a toxic substance. After the midterm exam, the student learns to make and solve simultaneous mass and energy balances for the moist air system using the Molière diagram for moist air. Dry and wet density, wet temperature, dew point and adiabatic saturation temperature are important terms, and the student should be able to do calculations for cooling below dew point, heating and mixing. It is crucial in this section to understand that mass balances cannot be made in volume units. The mass transfer section is the theoretically heaviest part of the course, and the student should be able to understand the molecular scale causes of the diffusion, estimate diffusivity in gases and liquids, as well as making calculations including diffusion and convection on the macroscopic level. We regard the link between diffusivity and mass transfer coefficients, which vary depending on which theoretical model that is most suitable, to be important for the understanding of this section, as well as being able to apply Reynolds analogy and the Chilton-Coburn analogy. In the compulsory task, the students determine diffusivity in air experimentally. The last section before the January exam is distillation. The simple compulsory lab is designed to help students understand what they are actually doing when using McCabe-Thiele's graphical method to do design calculations for a distillation column. Understanding the equilibrium stages, physical trays, overall tray efficiency and optimal feed location are important parts in this theme. In study period 3, the assessment is through a lab, study visits and 6 compulsory tasks, that is CT3 through CT8. In CT3, the students should look at some industrial process where mass and/or heat transfer are important and present a poster at a poster seminar. In CT4, the students model heat transfer in 3 dimensions using COMSOL multiphysics. In CT5, they interpret a process diagram and do design calculations for heat exchangers. There is also a short lab on heat exchanger to set CT5 into context. Before starting on CT6, the students first must learn theory related to transport in porous media. This includes how diffusion is similar mathematically to dispersion, what the difference is between the Darcy velocity and the real flow velocity. The students then model how organic chemicals leak out from an underground tank using a mass transfer equation including convection, reaction, dispersion and adsorption. In CT7, the students model bioreactions in a moving bed bioreactor using the mixing model continuously stirred tank reactor, that is a MBBR-CSTR. Finally, in CT8, the students do a simulation of CO2 levels in an actual lecture hall in one of the buildings at our faculty using COMSOL multiphysics.